We present temporal cascading of planning and control for Quadrotor MPC.
Many aerial robotics tasks require both rapid reactivity and long-horizon foresight. High-fidelity models provide precise control but are computationally prohibitive for long horizons. Low-fidelity planners scale well but sacrifice closed-loop performance. We introduce Unique, a unified MPC framework that chains models of differing fidelity within a single optimization framework. A short-horizon high-fidelity model ensures accurate control, while a long-horizon low-fidelity model accounts for recursive feasible plans to navigate challenging environments. To mitigate local minima induced by non-smooth clutter, we propose a 3D progressive smoothing scheme that gradually morphs norm-based obstacles along the horizon.
To escape local minima in cluttered environments, we run several planners in parallel with the main MPC. Randomly initialized point mass solvers explore different trajectories and converge over successive time steps. They're cheap enough to synchronize each iteration. A mixed integer planner tackles harder combinatorial cases asynchronously, since it's too slow to finish in one step. Whenever a parallel solution achieves a lower cost than the current tail, we reinitialize the tail with it, guaranteeing improvement by the principle of optimality.
In the following, we now present rendered visualization, including the reference track and virtual obstacles from real-world experiments, comparing standard MPC, a hierarchical planner controller baseline, and the proposed unique method. We begin with an agile trajectory tracking task where smooth obstacles obstruct the reference path. By combining long-horizon planning with high-fidelity agile control, Unique outperforms standard MPC by 22% and reduces the mean tracking error by nearly half relative to the hierarchical baseline. A second agile experiment, tracking a butterfly-shaped reference, shows that standard MPC increases tracking cost by 23%, while the hierarchical approach increases it by 274%. Next, we shift focus from agile flight to challenging navigation through numerous smooth blocking obstacles. Successful traversal requires both long-horizon planning and the proposed parallel initialization strategy to plan efficiently and escape local minima. The short horizon of standard MPC, along with the tendency of both baselines to become trapped in local minima, even with a long-horizon high-level planner, results in increased tracking costs of 52% and 44%, respectively. A second complex obstacle configuration highlights the inability of standard MPC to reach the latter half of a Figure 8 reference, degrading performance by over 300%. Similarly, the hierarchical planner yields suboptimal solutions, worsening tracking by 121% compared to the proposed method. Finally, we demonstrate the importance of progressive smoothing within Unique for non-smooth obstacles. This strategy enables numerically stable, tight navigation. In contrast, non-smooth cubic shapes cause severe convergence issues, while a fixed smooth over-approximation via a 2 norm leads to larger deviations around obstacles.
We validate Unique in a maze environment, both in simulation and in a real flying arena with Vicon motion capture. The drone has to traverse a tunnel blocked by randomly placed walls. Standard MPC can't finish the course at all. The hierarchical baseline gets through, but suffers cost spikes whenever the planner finds a new route and the tracking controller has to chase it and is unable to balance a general cost on quadrotor state. In Unique, this replanning happens smoothly inside the tail horizon. Across 40 randomized mazes, Unique with parallel solvers, and especially with the mixed integer planner, achieves the lowest closed-loop cost, clearly outperforming the hierarchical setup.
The manuscript presents a rigorously derived, recursively feasible formulation, compares alternative lower-level constraint approximations, and shows that simply increasing the MPC horizon cannot improve the Pareto frontier of computational budget versus closed-loop cost in empirical evaluations. As the approach is also robust to hyperparameters, it can therefore be considered as a novel standard formulation for quadrotor navigation, with no observed disadvantages over the baselines.